Hi, everybody. So it is October 10th for me in real time in what's going on in my world right now. But as you can see, the date down here in the title of this video is October 15th. That's because I'm anticipating being out of town on October 15th, 16th, and 17th. And also the 18th, incidentally, and the 19th and 20th, because I have a conference that I have to go to and attend in Southern California. So that's going to make it impossible for me to be in class and lecture to you all. So I figure as a replacement or a substitute that I would make some videos about this stuff and upload these videos to YouTube for your consumption. Now, a couple of notes about this. Oh, right. So we're going to be covering two topics: implicit differentiation, as you can see here, which will maybe take one or two lectures, maybe 1.5 lectures, is what I'm anticipating, and then the remainder of the lectures on video will be about related rates. And related rates is a pretty big topic. We want to do a wide variety of different problems. These are sort of represent the first real physical applications of the calculus that you've learned thus far to the quote unquote real world. And so hopefully will be of interest because it's actually very useful and a nice picture, a nice way or application of using all of this stuff that we've been learning. But that's a big topic, like I said. And so it's not going to be covered completely in 1.5 lectures or whatever it is that we'll be doing on video. So we'll have occasion to talk about it extensively next week. You will have a homework assignment, a web work assignment, covering these two topics in the same assignment. So we can, we'll hit both topics within that homework. But there won't be a quiz this week. Or by this week, I mean the week of the 15th. Yeah. Rather, we'll take care of all of that kind of stuff when we return. Or rather, when I return, because presumably you're still there on campus learning stuff. Yes? Okay. So I think, oh, can I say, I think it's important that you while you're watching these videos that you not just passively consume them, right? And that you really work while you are watching these things. So I really think it would be wise for you to have your notebook, to have a pen or a pencil, or if you're an iPad user, have your iPad, your Apple Pencil, or whatever they call those things. Take notes, just like you would in class, because taking notes is sort of the first pass at really trying to get this material inside of your brain. Another aspect of class that is going to be difficult to replicate in video are the moments when I'll ask you to, to do a problem, to do an exercise. When you're in class, you have some investment in actually doing it. What exactly that incentive structure is, I'll just sort of not say out loud. But we recognize that we're probably more motivated in the classroom setting to do these things. Well, I'm hoping that you can develop a kind of self-motivation to do those things while watching these videos. Because there will be moments where I'll say like, okay, pause the video here and try to work out this or that problem and see what you can make of it. So that when we unpause the video and I explain the solution, hopefully intelligently and hopefully correctly, you'll understand where you may have gone awry, or you'll get some new perspective maybe on solving the problem. Yeah, any number of things like that. But you have to be somewhat an active participant in all of that process. Yeah. There's a cliche that they say math is not a spectator sport, but which is dumb because math is not a sport at all. But I get what their meaning is. They mean that you can't just sit back and watch it and expect to know it or be a participant in it. You really have to, as they say, test yourself in the proverbial fire by trying, by actually putting energy and thought into it. And sometimes a video format like this can cause you to slip, not you, but cause you to slip into a kind of passivity. And we want to avoid that because I really want you to learn this stuff. Okay, that's enough of all that. Now, I will say that there is a worksheet that I've cooked up a while back, but cooked up about this topic that you could download from the Canvas page, maybe even print it off, and there are exercises in there. Let me show you what I'm talking about. Here it is. As you can see, implicit differentiation. There's some exercises here. There's some explication of this material, some motivation and all of that kind of stuff. And I'll be going over this. I wrote this thing, so this is sort of my perspective on this topic. But if you want to read this and work through it yourself, that's a great additional way to sort of try to get this material inside of your brain. And there are opportunities for you to do some exercises. And I believe on these exercises, I give you some of the answers. So you might work through these, see what you make of them, etc. Yeah. Good. But I'm not going to be working from this for these videos. Rather, I'm going to be working from pen and paper that you can, nope, not that one, that you can see here. Yeah. So here I've got my pen, I've got paper. This is real physical paper. I'm not fancy enough to yet have an iPad hooked up to my computer that I can then record video from. I just have never been able. It's not that I haven't. I just have never tried to get that setup going. I probably should figure that out because it looks pretty slick. But in any case, we're going to go this way. This is my COVID setup. This is the setup that I used during the pandemic when I was when we were all forced to go online and do our classes that way. But I'm replicating it here now for a much more tame reason, not because of an infectious disease that has killed millions of people, but rather because I'm going to LA. Okay, great. So what are we talking about? We're talking about implicit differentiation. That's the topic. Now, the opposite of the word implicit would probably be explicit, but nobody really talks about explicit differentiation. But if we were to talk about explicit differentiation, or if we were to contrast what isn't implicit differentiation, we would say it's everything that we've been doing since the start of the semester. That would be the sort of opposite of implicit differentiation. And so how can we frame what we've been doing so as to better contrast it with what we're gonna be doing, which is implicit differentiation? Well, here's the way I want to think about it. So we've talked about functions. We know that functions are a very, very important topic. There are lots of things which can be described using functions. For example, if you put a tea kettle on a stove and you turn up the heat, set the heat to some constant value, then you know that as time passes, the temperature in that kettle will rise, right? And you might conceivably construct a functional relationship between time, since the kettle was put on the stove and the heat was turned on, and the temperature of the water inside of the kettle. You might model that using a functional relationship. So how does this link up with the sort of ideas of functions that we were talking about before? Before, my perspective that I was trying to get you to understand about functions was as a input-output kind of scheme. That a function was a gadget for eating an input and spitting out an output. And that's totally accurate. That's like almost the definition. No, it is the definition of what a function is, with some words probably needed, like unique outputs and all of that kind of stuff. But that perspective is very much tied to this idea of, like, for example, the relationship between time and temperature of the tea kettle, the water inside the tea kettle, right? we have been talking about functions like f, okay, and we can feed this f quantities like x. And this x can be all sorts of different things. For example, it could be, in the case that we were just talking about, we might assign x units of time. That might represent time. It could also represent force. It could represent velocity. It could represent acceleration. It could represent mass. It could represent energy. It could represent any number of different things. It could represent money. It could represent, I don't know, calories. There's no shortage of things that we could represent with this variable x. And we could say that maybe there's a relationship between this quantity x and some other quantity y that is given by an equation like y equals f of x. Or I guess in this case, f of x equals y, whatever. These could be two different quantities altogether, different quantities, unrelated at first glance, but related through this kind of what we call functional relationship. So this is kind of a slight change in perspective from the input-output rule definition of function that we talked about earlier. Now I want you to sort of think about this kind of equation here, y equals f of x, as being like representing a relationship between these quantities. And I'm emphasizing that word relationship because we're going to use it again when we talk about related rates, okay? So we also know, by the way, this is sort of a representation of the graph of a function, the function f, right? This is the equation in the xy plane, the collection of all points x comma y, which satisfy this equation, is called the graph of the function. Yeah? And we talked about how to interpret in that situation or in that context the derivative of this function as the slopes of tangent lines to the graph of the function. Okay? And of course, we also talked about how the derivative represents the instantaneous rate of change in the values of the function. Well, okay. So with all that in mind, let's ask, is there a way of having a different kind of relationship between x and y? This is a very simple kind of relationship between x and y in some sense, but you could imagine there being more complicated relationships between x and y, but you would still be left with the question, what is the instantaneous rate of change in the function? How does changing the value of, let's say, x affect the value of y in a more complicated kind of relationship? Okay, what do I mean? This is where implicit differentiation comes in. So I'll just say, things like this might represent relationships. The relationship between two quantities, x and y. Sort of getting ahead of myself, I realize, with what I was saying earlier. That's okay. So you might, and if you're interested in how does y change as x changes, want to know how y changes as x changes, you can compute d dx of both sides. And we know d dx of f of x, that's just f prime of x. And on the other side, d dx of this is dy dx. Yeah. So this is what we've been, this is just more of the same thing. It's just different notations on either side. This is the instantaneous rate of change of y. That's the instantaneous rate of change of f, but of course y is f, okay? So this is the gadget we're sort of hunting for. We want to know how y changes as we change x, so we're sort of hunting for that. And it's simple in this situation where y is equal to f of x. It's simple. It's simply dy dx is equal to f prime of x. Okay, easy peasy, right? But what about more complicated relationships? For example, you could have two quantities x and y, and maybe they're related in the following way. X squared plus y squared is equal to 1. Now, I bet you've seen this kind of equation before in your life. You probably saw it because it turns out to be the equation in the two-dimensional xy plane, the equation of a circle centered at 0, 0 with radius 1. And let me draw a picture of that for you. So the curve will look something like this. Okay. This is the set of, in red, is the set of all points x comma y for which x squared plus y squared is equal to 1. The so-called unit circle, famous, right? Okay, well, you could view this as a relationship, this equation, as a relationship between x and y. It's a little bit different than the situation that we had up here. What is the main difference? The main difference is whereas here we could express y as a function of x, in this equation, in this relationship, that is not possible. And the reason is because if you tried to solve for y, just consider trying to solve for y. Let's do this calculation. I'm going to subtract x squared from both sides, right? And then I'm going to take the square root of both sides. Now, the square root of y squared, remember, is the absolute value of y. Okay, I'll write it. That's the absolute value of y. This side here is the square root of 1 minus x squared. And how can you have something solving this? Well, that's when y is either the plus or the minus square root of 1 minus x squared. This is just an instantiation of that proviso that whenever you take that fact, whenever you take the square root of both sides of an equation, you need to remember the plus and the negative branch of the square root, right? Okay. So what is this saying? If I give you an x in this equation, there isn't just one value of y that you obtain. There is in fact two values of y, the plus and the minus square root of 1 minus x squared. And that, well, if this is defined, and frankly, it's not always true, right? Because if x is 1, for example, then you get plus or minus 0, but plus 0 is the same as minus 0. So whatever. But, for some values of x at least, you're going to get two values of y out. That is a fundamentally different relationship between x and y as you would obtain in something like this. Because remember, there is no ambiguity about what we mean about when we say f of x. There's no two possible values or any of that kind of nonsense. We know that when we feed a function when we feed a function f and x, there's only one possible value that it could be. That's the way functions behave. But you can see from the graph, it's not even a graph. You can see from this curve, which is the set of solutions that x squared plus y squared equals 1, which also incidentally is the set of solutions to this equation. You can see that for a particular value of x, like say this one right here, this value of x, there are in fact two possible values of y. And those correspond to the plus and the minus branch of this square root here. Okay? Nonetheless, we still might be interested in, let's say we are here. Let's say we know the state of a system and say that state of the system is right here. So it's at this xy value. that xy value satisfies this equation. And let's say that we change let's say we change x a little bit. We want to know how y changes. Now you can see that if we change x a little bit, we move either down the maybe clockwise down this circle, or maybe counterclockwise along the circle. But in particular, in some kind of way, the value of y changes, right? And we want to understand what that relationship is between how y is changing as we change x a little bit. Okay, that's the idea. And so what we want to know is what dy dx is. So let me write a little bit about this. This equation gives a relationship.
Hi.
Oh, hi. I'm recording a video right now.
Okay.
This equation gives a relationship between x and y. And so we can ask the question, how y changes as x changes. In other words, and let me move up here now. Oh, this is a little bit weird. In other words, let me make sure it's all on the screen. Yep. What is dy dx? So given this equation, we ask the question, what is dy dx? How does y change as x changes? Yeah. Okay. So maybe I'll frame that as a question. Q. Q for question. Do you know Q is the first letter of the word question? Now so the next thing I'm going to do is I'm going to write the letter A. And you know why? No, don't pause. It's because A is the first letter of the word answer. So what's the answer here? Well, to find it, you should take this equation, which is the relationship between x and y, and d dx both sides. So here's the method. Take d dx of both sides of x squared plus y squared equals 1. Okay, let's do this. So I'm going to just literally d dx both sides. X squared plus y squared is equal to d dx of 1. Now, one of these is incredibly easy, namely d dx of 1. 1 is a constant, after all, so it dies. It's 0, in other words. Okay. All right. What about d dx of x squared plus y squared? Well, we know by the sum rule, yes, that this is equal to d dx, I'm going slow, of x squared plus d dx of y squared. Yeah? Well, d dx of x squared is easy peasy. Why? Because of the power rule, right? The derivative is just 2x. I hope that is not controversial. What will be more controversial, almost certainly, is what's happening with this other term here, d dx of y squared. And the reason that that's controversial is, well, you might think that the answer is just 2y. And that's what you would spit out if you were just sort of like an involuntary, like an unthinking automaton. And you just, whenever you see y squared, you just invoke the power rule. But you need to be a little bit more thoughtful about it than this. What we are implicitly, and hence the word implicit, kind of the word implicit differentiation. Maybe this is the motivation for that word implicit being there. What we are doing is we are kind of implicitly thinking of y as a function of x. Y, in other words, depends on x in some way. And we're not being explicit about how y depends on x. We're not expressing the relationship between y and x like this, where y is explicitly defined as a function of x. No, we're only implicitly examining that relationship through an equation like this one. Okay? Now, what then is the right way to think about this gadget here? I'm going to pause. I suggest you pause and think about it. Okay, did you think about it? Okay, now I'm going to say the answer, the two-word answer, and then I want you to pause and think about that. Here it is, chain rule. Okay, now pause, think about it. Okay, did you unpause and think about it? Okay, so what is this? What does the chain rule tell us this is? Let me tell you. The chain rule says that this is equal to ddx of y squared. You know what we can do? We can first do ddy of y squared. And then multiply the result by dy dx. Yeah. Now, it's almost like, it's easy to write this down, chain rule, because it's like the dy's cancel one another. And there are calculus teachers out there that will say, tisk, tisk, these aren't fractions. And you know what? This is going to go out on the internet, right? In public. I'm right. Okay, you can treat these for right now like they're fractions, okay? And you will not go wrong unless you do something truly obscene. But in particular, for this particular operation that we're doing, it works out just fine because of the chain rule. Because the chain rule allows you to make that kind of quote-unquote simplification or quote-unquote cancellation, okay? All right, let's dispense with all that. Now, if I asked you what was ddy of y squared in isolation of everything else in the world, you would know immediately what that was, right? That's 2y by the power rule. So that's what it is here. But now I want you to see what we've got. We've got an equation that involves dy dx. And do you remember what we're hunting for? Look up here. Look at the question. What is dy dx? Well, there's dy dx. What we can do is solve for dy dx. So I can subtract 2x from both sides. And then I can divide both sides by 2y. I can cancel the 2's, so I end up with negative x over y. That's dy dx. Now, I want us to observe a couple of things about this. This dy dx depends on both the x coordinate and the y coordinate. Remember, when we had a relationship like y equals f of x, like imagine f of x here is like x squared. Dy dx would be 2x, right? In other words, the derivative of y would depend on x only. And the reason for that, one perspective on the reason for that, is because every x corresponds to exactly one y, because of this relationship between x and y. But now when we're dealing with a more complicated relationship, that is no longer the case. If you give me an x, like say x equal to 1/2, there are two possible values of y. So if you're going to tell me what the instantaneous rate of change is of y with respect to x, if you're going to tell me that, you have to tell me both, because the answer is going to be different whether or not I'm here or I'm there. So telling me x alone is not enough. Another way of saying all of this is look at the tangent lines to the graph, not the graph, this curve. Look at the tangent lines to the curve. There's that one there. But then there's also this one here. They both correspond to the same value of x, but different values of y. The slopes are different of these tangent lines. So you need to know both x and y in order to figure out which of these tangent lines you're even talking about. You with me? Okay. In particular, using this, actually, before we keep going, let me just point out that this is consistent. This result here is consistent with what we see to be true about the familiar unit circle. So there are 4 points that we understand really well. Those are the 4 compass points. If we view this thing as a compass, like this is the North Pole. And what are the coordinates of the North Pole? It's not the best picture. What are the coordinates of the North Pole? 0, 1. Very good. I know you just said that to your screen like a lunatic. And if you plug in 0 and 1 into dy dx here, if you plug in x equal to 0 and y equal to 1, what do you get? You get 0. Now, doesn't that make sense? Because isn't the tangent line to the red circle at the North Pole at 0, 1, isn't that 0? Or horizontal, I mean. So 0 slope, I mean. Did you understand what I just said? I can't. Okay, I don't understand what I just said. When you plug in 0, 1 into this expression here, you get dy dx equal to 0. In other words, what that would be saying is that the instantaneous rate of change of y with respect to x is 0. Another way of saying the slope of the tangent line at 0, 1 is 0, which is true for the circle. This isn't the greatest picture of a circle, but whatever. And it's also true about the South Pole as well. The tangent line down there is also horizontally sloped. That has coordinates 0, -1, and this fraction would be 0. Another thing to observe, what's happening at the east and the west points of this compass? Like, let's take the east. No, is that east? Yes, east. The coordinates of east are 1, 0, 1, 0. So if we plug in 1 and we plug in 0, do you notice that we get something undefined? Division by 0 error. And do you notice that if we draw the tangent line here, we get a vertical line? And did you know vertical lines have no slope? They have no slope. So it's all consistent, right? It's consistent with that. In other words, you could detect where the vertical lines are in this picture here by figuring out where this quantity here is undefined. Great. How long has it been? Okay, I've got about 18 minutes or so. Well, let's do an exercise using this insight that we just generated. Let's find the equation of the line tangent to the curve. What curve? X squared plus y squared equals 1. I guess that's not a curve, but you know what I mean. The curve described by that equation. Find the equation of the line tangent to the curve that at the point. Well, now we have to find a point which lies on this thing. How about the point square root of 3 over 2, 1/2? Now, you can check that if you plug in x equal to square root of 3 over 2, and you plug in y equal to 1/2, that it will indeed be, the sum of the squares, basically, of these two numbers here will indeed total up to 1. So, in other words, this really is a point on this red circle. It's like right there-ish, where the tip of my black pen is pointing, somewhere around there. And it was easy for me to come up with these values because you know what I was thinking inside of my brain? I was thinking inside my brain, this is exactly cosine of pi over 3. Let me make sure that's right. No. Huh? Wait. I pointed to the wrong place. root 3 over 2 is like, and 1/2 is like right there. It's not up there. It's like at 2 o'clock and not 1 o'clock on an analog clock. Clock. 2 o'clock. Sorry, it felt like I said the word clock a lot of times in a row, but that's because I did. Okay, it's at 2 o'clock. 2 o'clock on an analog clock. So this is at pi over 6. My bad. I messed up. And you know what that is? That's at sine pi over 6. Or that's equal to sine pi over 6. The y coordinate of, yeah? And if you remember us talking about trigonometry and how the unit circle is the most important picture that you need to have inside of your brain in order to understand trigonometry, you'll understand how I knew immediately that that point would be a point on the circle. Okay. Yeah, so let's solve this problem here. All right. So how? So as usual, what we're going to do is find the slope of the line and a point which lies on the line. Now, a point is kind of given to you for free for no work. That is the point on the line that we know, or that is the point on the circle that we know that the line passes through. Because after all, this line is tangent to the circle at that point. Okay? But the slope we need to figure out. The slope we can obtain by looking at dy dx, which BTW is that. We're going to take dy dx, and we're going to plug in the point, this, root 3 over 2, comma 1/2. And this is that vertical bar notation that I was telling you about. This is very commonly used when we use Leibniz notation for derivatives. And this means that you plug in for the x coordinate, root 3 over 2, and plug in for the y coordinate, 1/2. So looking back at what dy dx is, it is negative x over y. So we're going to evaluate this quantity at root 3 over 2, comma 1/2. Okay. How did I come up with this relationship? That just came from the previous page. Okay, so rewind the video if you've forgotten. And then we plug in. So what we get is negative root 3 over 2 upstairs, and downstairs 1/2. Now, fractions inside fractions are upsetting for everybody. So the way that we work with this, this is good, is to take the thing in the denominator, flip it upside down, in other words, take its reciprocal and multiply by what's in the numerator. So this is the negative root 3 over 2 times 2 over 1. The 2's die, and we're left with negative root 3. And that's the slope of the tangent line. Great. So now we know the slope, and I'll just record the fact that we know a point too. We know that the point is root 3 over 2, comma 1/2. And so now in principle we know everything. Because remember that thing? If we have a point h comma k on a line and with slope m, then its equation is given by y minus k equals m times x minus h. Well, we could use that here. So we have y minus 1/2 is equal to root 3 times x minus root 3 over 2. And if we wanted to get this into that slope intercept form, then we could add 1/2 to both sides, distribute the root 3. So I get root 3x. I'm going to add the 1/2, but just chill out. And then root 3 minus root 3 over 2 is minus 3 over 2. Right? The root 3 times root 3 is 3. And then we add 1/2. And then finally we can simplify this to be minus 1. Wait. That hurts my feelings? Oh, you know what I did wrong? That hurts my feelings for reasons that I won't describe to you. But I made a mistake. Pause the video. Scrutinize. Where did I screw up? It's good practice for you because this will inevitably happen to you someday. And you'll be wondering, like, Where's the bug? Where's the tiny little mistake that screwed everything up? There is a tiny mistake that screws everything up. You see it? Pause the video and find it. Oh, wait, did you find it? Yeah, it's this. It's that negative sign. I just forgot it. Okay? Oops. If I had any shame, I'd feel terrible about it. But in particular, when I distribute the negative root 3, this becomes positive 3 over 2. And so in particular, positive 3 over 2 plus 1 half, I think that's 2. Yeah. So I think that's right there. Okay? That's the equation of the tangent line. All right. Let's do another one. And I'm going to do the one that's sitting as exercise. Well, no, I'll do the example here. Find the equation of the tangent line. So this is This is the first example, or maybe the second example, in that worksheet that I was linking you to in the Canvas shell. Tangent to the curve x. Oh, that's not how you spell that word. That's good. Xy squared minus x squared plus 2y equals 2 at the point 1, 1. This is a little tricky. Okay. What we're hunting for is dy dx because we want to know something about the slope of lines tangent to this graph. Not graph, this curve. Okay? So we're going to the way that we're going to try to figure out what dy dx is to d dx both sides of this equation. So solution, first find dy dx. And this is the process called implicit differentiation through implicit differentiation. Yeah, I should be clear about what we call this process. It's called implicit differentiation. So first, I'm going to take d dx of both sides. And if I do that, that means I'm looking at d dx of all that mess. And then that's equal to d dx, of course, of 2. Easy bit first, d dx of 2, because 2 is a constant, is just 0. Harder bit, and actually, yeah, harder bit, is what's happening here. Note that this xy squared in particular is a little bit, well, okay, let's go slow. It's okay. Let's first use the sum rule, yeah, to break up these into pieces. So this is d dx of xy squared, and then we have minus d dx of x squared. That's not how you write x squared, plus d dx of 2y. Okay. This requires the product rule. I won't hold you in suspense. This requires the product rule. And that's because it's the product of two natural pieces, x and y squared. And we're going to use the product rule to evaluate it. Now, I'm going to talk through how this works rather than doing really good bookkeeping as I usually like to do. I'm assuming that we've graduated past that. If you haven't, it's okay. Do the bookkeeping. But if you're okay with it, I'm just going to talk it out. The derivative of xy squared is the derivative of x, which is 1, times the other piece left alone. So that's y squared. Then we add to that x times the derivative of y squared. Now I'm going to write that as d dx of y squared for a moment. Okay? And we'll work on it in a bit. Let's go through the other pieces real fast. What is the derivative of x squared with respect to x? That's just 2x by the power rule. That's easy. And what's d dx of 2y? Well, remember, just like up here, when we were taking the derivative of something involving y, it was useful to use the chain rule. First take the derivative of y squared with respect to y, then multiply by dy dx. So we're going to first multiply this by the derivative with respect to y of 2y. You know what that is? That's 2. And then we're going to multiply that by dy dx. I would say that if you didn't understand how we went from here, you see where my finger is pointing? Or let me box it. This became that. Then I would like you to rewind the video however many seconds, 30 seconds, and just watch that explanation again. Maybe I'll say it one more time for you right now. By the chain rule, the derivative of 2y is the derivative with respect to y of 2y, which is 2, times the derivative of y with respect to x, which is the dy dx that we see there. Okay. Let's keep going here. I've only got 4 minutes. This y squared stays the same. I don't have to do anything with that. This part here, though, this part. So I have x times, now we're going to use the same logic. The derivative with respect to x of y squared is the derivative with respect to y of y squared, which is 2y, times the derivative of y with respect to x. That's the chain rule again. Exactly the same gadget. And then we write the rest of this garbage down. Okay? Now what we're going to do is solve for dy dx. Because let's say that the question instead of asking about this tangent line here, let's say it asked for what dy dx is. Well, we could obtain it from this equation by solving this equation for dy dx. Okay, so let's do that. How? Well, it's a strategy that you've hopefully cultivated from algebra of getting everything that involves dy dx on one side of the equation and everything that doesn't involve dy dx on the other side of the equation. So I've got these two terms. I'm going to leave those on the left-hand side. I'm going to move those two terms, though, over. And if I do that, I get x times, or I'm going to write this as 2xy. And actually, I'm going to factor out the dy dx. So I'm going to do kind of two moves at once. You scrutinize this if it doesn't make sense to you. Okay? That's what I get with these two terms. And then those two terms I move over, and I have 2x minus y squared. I'm moving fast in the interest of time. I'm not going to be able to finish this tangent line problem, but hopefully I'll be able to finish this. Okay? And then we have dy dx. We could solve for dy dx by just dividing both sides by 2xy plus 2. Like this. And that's dy dx. And that's not the answer that I'm looking for, because that wasn't the question. The question was about equation of a tangent line. But this is an important first step. Why? Because what we're going to do with this is plug in the point 1, 1 to obtain the slope of that tangent line. And because we know that 1, 1 lives on the line, we can then figure out what the line is. It looks like I'm just hitting about 50 minutes now. So here's what I want to say. I want you to try to figure out what dy dx, or sorry, no. I've already done dy dx. What I want you to do is to figure out what that equation of that tangent line is. And try to get it in the form y equals mx plus b, that form, where m is the slope, b is the y-intercept, etc. Okay? The next video, we will solve that problem and say a little bit more about implicit differentiation. You'll get some problems about this on your web work so you can practice. The key thing are these transitions where we go from d dx of 2y to 2 dy dx, or from d dx of y squared to 2 dy dx. That's the spirit of implicit differentiation. And what is lies at the heart of it is just the chain rule. Okay, see you next time. Bye bye.